Hi guys, this is Dr. G here, and in this particular video we will talk about another very popular electrophilic aromatic substitution reaction, and namely this reaction is known as Friedel-Crafts alkylation. Okay, so using this Friedel-Crafts alkylation, you can easily uh, substitute a hydrogen in your benzene ring or in your aromatic compound from an alkyl group. Okay, so this reaction is extremely important if you wanna substitute a hydrogen with an alkyl group. So let's see how you can do this. Okay, let's see how you are going to achieve this. For this particular reaction, you are going to need two things. Okay, you are going to need two things. First, you are going to need an alkyl halide. Okay, alkyl halide. And then of course you are going to need aluminium chloride as your catalyst. Okay, so AlCl3 is going to act as your catalyst, and then you will also need an alkyl halide. And also please remember to use or select the R group in such a way that this R group will be the same R group you will get in your substitution reaction. So be mindful when you are selecting the alkyl halide, because the R group of the alkyl halide will be the substituted R group on your aromatic compound. All right, so let's see how this reaction is going to occur. Okay, first of all, since this is an electrophilic aromatic substitution, okay, since this is an electrophilic aromatic substitution, you are going to need an electrophile. You are going to need an electrophile. So what is an electrophile? Electrophile means a species that loves electrons, or in other words, a species that is deficient in electrons, so therefore it will like electrons, right? So in this case, the electrophile is going to be a carbocation. Okay, so basically when you react your alkyl halide with AlCl3, okay, AlCl3, the AlCl3 is going to take the halogen from the alkyl halide, giving you a carbocation, of course, because of the positive charge on carbocation. This species, this carbocation, will be your electrophile. Okay, so let's see how you are going to use this electrophile, right? So here is our benzene. Okay, here is our benzene. So benzene will basically attack the electrophile. Okay, benzene will basically attack the electrophile by using the pi electrons. Okay, and then you will get another carbocation, but this time the positive charge will be on the cycle. Okay, the positive charge will be on the ring. But here is the problem. Okay, the aromatic compounds have a conjugated pi electron system. Okay, so therefore they are very stable, but once it takes an electrophile by using the pi electrons, you no longer have a conjugated pi electron system. Okay, so basically it will lose the aromaticity. Initially you had conjugated 6 pi electrons on benzene, but now you only have 4 pi electrons, so therefore it is no longer aromatic, right? So this intermediate is therefore extremely unstable as compared to your aromatic compound, and therefore it will immediately react with AlCl4 minus. Okay, it will immediately react with AlCl4 minus and then regenerate the aromaticity by taking the carbon hydrogen bond electrons into the ring. Okay, so when that happens, you will basically get your ring back. Okay, the aromatic ring back. All right, so of course the byproducts will be HCl and AlCl3. So this is how it is going to happen, and I'm pretty sure you guys are familiar with drawing resonance structures for this intermediate. Of course, this intermediate could be somewhat stabilized by going through resonance stability, right? So resonance stability. So how do you do that? You can use these two double bonds and you can delocalize this positive charge into the ring. By doing that, you will the molecule will reduce the instability uh, by a little bit. Okay, so even though it is more unstable as compared to benzene, it can achieve somewhat stability by delocalizing the positive charge through resonance structures. All right, so this is the reaction. So let's try another reaction. So let's use benzene and react it with another alkyl halide. In this time I'm going to use, let's say, this particular alkyl halide, and then AlCl3 should always be there. That is your catalyst. Okay, so what will be the product? Okay, so you are basically substituting a hydrogen from benzene with the alkyl group, right? So let me draw this alkyl group in a different color so that it will be easy to figure out. Okay, so let's say one of the hydrogens on the benzene ring, excuse me. So one of the hydrogens on the benzene ring will be replaced or substituted by the R group, okay? So this is the product that you get. Okay, this is the product that you get. And of course the byproducts will be HCl. All right, so this is how you understand this reaction. So this is a very straightforward reaction. So basically the R group on alkyl halide will be substituted into benzene. Okay, will be substituted into benzene. Okay, by giving you a substituted benzene. So here's the problem. Even though this reaction looks very straightforward, there are plenty of limitations. Even though it looks like an ideal reaction to substitute an R group into benzene, there are plenty of limitations. So let's talk about these limitations in more detail. So the first limitation that we are going to talk about for Friedel alkylation is that whenever you have a monosubstituted benzene, okay, so if your benzene has a substituent already attached to it, that substituent could have a negative impact on the Friedel alkylation. Specifically, if this substituent is something like an amino group, okay, it could be an NH2, or it could be a NH and a sub R group, or then the nitrogen could even have two R groups, okay? Or if you have a very strong electron withdrawing group attached to benzene group, then basically this Friedel alkylation could have a very negative impact. So basically, if you have an electron withdrawing group such as, let's say, aldehyde group, ketone group, okay, any strong electron withdrawing group could have a negative impact on this reaction. Okay, let's say carboxylic acid. I mean, we are going to talk about these electron withdrawing groups in more detail later on, but for now, I mean, just remember some of these electron withdrawing groups. They are going to be more than enough. Okay, so usually if you have an electron withdrawing group or an amino group directly attached to your benzene, then the substitution of R group using Friedel alkylation will not work. So you will not get this product. So there will be no reaction. Okay, so it will be no reaction. All right, so that is the first limitation, and of course there are two more limitations. Okay, so the second limitation that we are going to talk about is called polyalkylation. Okay, is called polyalkylation. In a later lesson, we will learn that alkyl groups basically activate benzenes or aromatic compounds. So alkyl groups basically activate benzene groups. So in other words, it will basically uh, stimulate the benzene group to get more and more alkyl groups attached. As an example, let's say you are using an alkyl halide like this. Okay, so AlCl3 will be our catalyst, and then the desired product will be the third butyl group directly attached to the benzene, right? So this is the desired product, but it will not stop here. This alkyl group can actually activate the benzene group to have additional R groups. So basically it can further substitute alkyl groups, in this case third butyl groups, into benzene. Okay, so rather than getting one R group, you might get poly alkyl groups. Okay, so more than one alkyl group. So because of that, you will not get the desired product. Okay, it will not stop in this mono substituted alkyl benzene. Instead, it might get more than one alkyl group substitutions. So that is the second limitation. So let's go back and revisit the limitations. First, if you have a monosubstituted benzene with an electron withdrawing group or an amino group, okay, you might not be able to do this Friedel-Crafts acylation, because these electron withdrawing groups or amino groups can basically poison the benzene ring towards electrophilic aromatic substitutions. So the second limitation is actually polyalkylation. So that means the benzene group may get more than one alkyl group attached to the benzene ring. So we call it polyalkylation. So in fact, the monoalkylated product will be the minor product. Okay, most of the times the major product will be a polyalkylated compound. All right, so the third limitation is also very common. Okay, that limitation arises due to the rearrangement of your electrophilic carbocation. Okay, so we learned that our carbocations, let's say we have an alkyl halide like this, and then we are reacting it with alkyl halide, right? I mean aluminium chloride, and then you will get an electrophile, which is a carbocation, plus AlCl4 minus, right? So the carbocation that you get, okay, it might rearrange. Sometimes these electrophilic carbocations have a tendency to rearrange, especially based on the stability. So this carbocation right here, it is a primary carbocation, right? So if you remember the carbocation stabilities, tertiary carbocations are the most stable, and then the secondary carbocations, and then primary carbocations, right? So this is how the carbocation stabilities vary. So tertiary carbocations are the most stable, and then secondary, and then primary. So in this particular carbocation, okay, in this particular electrophile, you are getting a primary carbocation. So primary carbocations are not that stable, but if this molecule undergoes hydride shift, okay, if this molecule undergoes hydride shift, then easily this primary carbocation will be converted to a secondary carbocation, right? This primary carbocation could be converted to a secondary carbocation, which is more stable. So based on the stability of the carbocations, okay, excuse me, this is a secondary one. So based on the stability of the carbocations could rearrange, and then the product that you get could be different. Okay, the product that you get could be different. So if you have this particular carbocation, your product will look like this. Okay, so your product will look like this. This will be your major product. Remember, you were expecting to have a propyl group directly attached to benzene, right? Instead, you might get a isopropyl group. So this will be a minor product, this will be the major product. All right, so these type of rearrangements are very common in Friedel-Crafts alkylations. So my advice to you is that whenever you have an alkyl halide, okay, always look at the electrophile. Okay, always look at the electrophile. As an example, if you use this particular alkyl halide, okay, once it reacts with AlCl3, it will produce an electrophile which is actually a primary carbocation. It is not that stable. But if there is a methyl shift, this primary cation could be converted to a tertiary carbocation. It could be converted to a tertiary carbocation. Okay, so this tertiary carbocation is much more stable as compared to the primary carbocation. So whenever you are doing Friedel-Crafts alkylations, always take a look at the electrophilic carbocation, and if it is a primary one, see if you could get a better or more stable carbocation by rearranging the carbocation using either hydride shift or alkyl shift. Okay, so always look for hydride shift or alkyl shift. Okay, so by doing those two things, you can actually identify the possible rearrangements for carbocations. Okay, so if you use this particular alkyl halide, okay, you will ultimately get a product like this. You will ultimately get the benzene directly attached to the tertiary carbocation. Okay, so this will be your major product. Okay, what will be the minor product? The minor product will be the benzene attaching to the primary carbocation. So this will be your minor product. Okay, so that's pretty much everything that I want to mention in this video. Okay, so once again, in summary, this video discussed about Friedel-Crafts alkylation. This is an electrophilic aromatic substitution where you substitute a hydrogen in benzene with an alkyl group. Okay, so this is a pretty straightforward substitution using a carbocation electrophile, but of course there are some limitations to this substitution. Okay, there are some limitations to this substitution. One of the limitations is that if you already have a monosubstituted aromatic compound or a monosubstituted benzene, that substitution could impact the substitution of the alkyl group. So keep that in mind. Secondly, alkyl groups are activators of benzene rings. So when one alkyl group is already attached to the benzene ring, it can catalyze, it can have a positive impact on further substitutions. So you can get poly-substituted benzenes. And the third limitation is the most important one. Okay, so when you are trying to attach an alkyl group into benzene, always look for the carbocation stabilities, because based on the carbocation stabilities, your alkyl group could rearrange. Based on your carbocation stabilities, your alkyl group could rearrange, and therefore the major product will most probably be from a rearranged alkyl group rather than not rearranged product. Okay, so keep those three things in mind. So there will be plenty of examples for you to try in your quizzes. So please feel free to contact me if you have any questions. Okay, you guys have a good one. Take care.